Okay. Yeah, welcome all. It's a pleasure for me to introduce this public talk by Professor Eric Herbst from University of Virginia. So this is a public talk on astrochemistry, and we are going to take questions at the end of the talk through the YouTube channel, and I will give the word to Paola, who has a short introduction on Eric. Thank you.
Okay, so thank you very much for giving me this opportunity. So first of all, let me say good morning, good afternoon, and good evening to everybody, actually to all the astrochemists in the world, and especially those who have followed the KROME school. So I am Paola. You saw me on Monday to give some lecture on astrochemistry. But the most important thing is that I had the fortune to spend 9 months of my life actually in the group of Eric Herbst, and this was done during my PhD. So in fact, I'm very much honored and excited to introduce you Professor Eric Herbst, who is, I would say, the father of astrochemistry. So what else we can have? This is the best we can do here, to have a public lecture from Eric. So Eric received his PhD in physical chemistry from the Department of Chemistry at Harvard University under the Professor William Klemperer, and this was in 1972. And in fact, during his PhD work, he showed, among other things, that ion-neutral reactions, so reaction between ions and molecules, which have very fast rates and independent of temperature, they are among the most important reactions that can happen in the cold interstellar clouds where stars and planets form. In 1980, he moved to Duke University as associate professor of physics and was subsequently promoted to professor of physics. In 1991, he moved to the Ohio State University, initially as a professor of physics. Well, then in 1992, I joined his group, but this is not in his CV, it's in mine. In subsequent years, Eric Herbst received the secondary appointments in astronomy and chemistry. He's now a Commonwealth professor in the Department of Chemistry and Astronomy at the University of Virginia. Eric Herbst is specifically interested in the chemical processes by which molecules form and grow, in using these chemical processes to predict the actual concentration, abundances of molecules in space, and in the role of molecules in understanding the physical environments, so clouds and interstellar medium. He has a long-standing experience in different aspects of astrochemistry, from rotational spectroscopy to modeling, calculations, and observations. Eric Herbst has won a number of international prizes, including the Johannes Marcus Marcy Medal and the Centenary Award of the Royal Society of Chemistry in the United Kingdom. And he is a fellow of the Royal Society of Chemistry since 2004. So let me just finish saying that Eric is just an inspiration for all of us astrochemists. And without taking any more minutes, I'll leave you with him, who will talk about astrochemistry now and then, the current state of the subject and its amazing development.
Well, thank you very much, Paola, for that a great introduction for me. I don't know if I'm the father of astrochemistry, but the older people are mostly no longer with us, so I guess I am in that sense. So the title of my talk is Astrochemistry Now and Then, the current state of the subject and its amazing development. And what I'm going to do is to give you a rather lighthearted talk on both the science and its history. And I'm hoping that the level of the talk is suitable for a wide and diverse audience. So let me now start. Okay. What is astrochemistry? That's a good way to start. In any case, so I go to Wikipedia, which is the standard encyclopedia of the day, and it tells me that the study of chemical substances and species occurring in stars and interstellar space. Well, I guess that's okay. I'm not quite sure what the difference is between substances and species. So I went to Siri. I carry an iPhone, and Siri's supposed to answer all questions, but what did Siri do was say to see Wikipedia. So anyway, I thought I'd give my own definition, most of which Paula has already mentioned. First, the use of telescopes to find molecules throughout the universe by their spectra, which are collections of radiation unique to each molecule. Second, the study of chemical reactions outside of the Earth and the solar system. And third, the study of the role of molecules in understanding the birth, life, and death of stars and matter in between. Molecules are indeed the best probes of cool and warm regions of space. All right, so who studies astrochemistry? Well, a lot of different people. First, there are astronomers. Astronomers find the molecules in space using telescopes. Then there are chemists. Chemists, I guess, have two roles. One is they study reactions, so they study how the molecules are produced from atoms and grow. And the second group actually measure so-called spectra in the laboratory, spectra being collection of electromagnetic waves, mostly radio waves, and without knowledge of such spectra, we are not able to detect molecules in space. Then there are physicists, and they study how physical effects alter the chemistry, among other things. For example, when dust particles accrete into planets, and certainly that changes the chemistry a lot. Now we can divide chemists up into two types, experimentalists and theoreticians. Experimentalists get their hands dirty, studying molecules and chemical reactions. And theoreticians, of course, prefer to use computers to do the work. So let's start with a brief introduction to that portion of astronomy that's important for astrochemistry. We start off with the basic knowledge that the universe has lots of matter in it. Much of the matter is in the form of large galaxies. To quote the late Carl Sagan, billions and billions of stars. And you're looking at for the most part, a nearby galaxy. Nearby in space is still many, many light years away, but relatively nearby. So you get a good view of it. And what you see is in this flat structure are mostly stars. Stars are hot, and so they're bright and they emit in the visible. So the eye can see them. Sometimes you can't see them resolve one star from another, but you see the bright light, and that's the stars. But in addition to the stars, about 10% or so of the matter in a galaxy such as Andromeda and our Milky Way, about 10% is in between stars in the form of gas and dust, much of which is collected into what we call interstellar clouds. Interstellar clouds are very interesting for a number of reasons. First, chemically, that there are lots of molecules there. And of course, if there are lots of molecules, that's what astrochemists like to hear. But seeing these clouds in the Andromeda picture is not very easy. So I go to our own galaxy, and this is a rather spectacular and recent picture showing in the direction of our own galaxy, the Milky Way. The Milky Way is also a name for the center of the galaxy, and you can see all the white material. That's again, bright stars. But you can see something there in front of it that's blocking them. And these are types of interstellar clouds that are dense and dark, and the light can't penetrate through them. Now, the clouds have both a gaseous and a solid matter inside them, the solid matter being dust particles, and it is these tiny dust particles that block most of the visible light. And so these clouds do appear black. Now, astronomers wanting to determine if molecules are there or not cannot use classical astronomy, because in the visible, where stars shine, all that light is blocked by the clouds, and so we don't see it. It turns out that the types of waves that astronomers like to use to see molecules are radio waves. There are also infrared waves, but radio waves are the dominant way of looking for molecules in interstellar space. Radio waves can go right through dusty layers, and so we can use them to study the molecules that are in these clouds. All right, moving closer to another dark, dense cloud, and this is in the constellation Taurus, and I think I have it approximately right as to where it is. What I want to say here is that these dark regions, which you can't, of course, see in the visual, are understood to be very heterogeneous. So there are regions that are more dense, and there are regions less dense, and one of the densest and interesting regions in smaller regions is called the cold core. And the one you're looking at in particular is called Taurus Molecular Cloud 1, or TMC1, which has a very, very low temperature and a very, very low density. Now, if you're not familiar with Kelvin, 10 Kelvin is about minus 260 Celsius and is only 10 degrees above the absolute of 0. So all the molecules moving around in the gas are very sluggish at this temperature. Now the N is the gas density, and that's 10,000 atoms and molecules per cubic centimeter. Now that may look like a big number to you, but it's very, very small. And this tells you that it's a very good vacuum compared with what we have on Earth. In any room where you are now, the density of molecules is orders and orders and orders of magnitude greater, and collisions between molecules occur billions of times each second. This is not what happens in space, where collisions are very few and far between, but these dark clouds, especially the cold cores, actually, they live long enough that there is a chemistry that does occur. And we see it mostly by observations in the radio. All right, now there's something very interesting about interstellar clouds and stars. They are sort of connected together in the following sense, that old stars give birth to clouds, and old clouds, portions of which collapse, give birth to new generations of stars and planets. Okay. Now I'm showing you a cycle. It's a little oversimplified, but it does give you the basic picture. And to go through all these stages between stars and clouds and stars, we have this diagram, and it shows as if things are, one stage is moving to another one, but that's not really right. I mean, you're not supposed to think of motion, you're just supposed to think of time increasing. And there is some motion, but mostly we're not talking about going from one portion of space to another. We are actually, in a sense, because astronomers can't really see time very well. So all these different evolutionary stages, come from different places. But what's really happening is that time is increasing. So let's start with a stellar system, which is in the lower right here, like our solar system. What happens initially is stars get old. And well, our sun will be old in about 5 billion years. And what happens next is that when it's old, it really will give forth a lot of matter. It gives off some matter now, but a lot of gas and dust is formed. It goes through several stages I've not shown, and eventually makes so-called wispy clouds called diffuse clouds. And one can actually see through these clouds, unlike through the denser ones. But gravity eventually converts the diffuse cloud into a dark, dense cloud. And this is, I'm showing here my representation of what you've already seen in reality. And just to mention, to remind you that these are heterogeneous regions, even if they all look black, but there's something called a prestellar core, follows a cold core and is actually collapsing to form a star. But first, the collapse actually stays cold, And a lot of molecules in the gas phase accrete onto dust particles, but eventually things change and the temperature warms up and a star begins to form, and it's called a protostar. Proto means in the act of formation. And eventually the material around it heats up and sort of collapses into it. And we call these regions hot cores rather than cold cores. And a lower temperature for a hot core might be something like 300 Kelvin. But of course, right near where the star is forming, the temperatures would be much higher. Now, the material in the hot core actually is indeed collapsing, and it could collapse into the star, and that's the end of it. But also, if it has what's called angular momentum, it could form a planar object called an accretion disk. Now, the accretion disk is revolving. The dust particles in the gas are revolving around. Now, it's almost a star. And the next thing that happens eventually is all the dust that's going around the star actually accretes into larger objects. So this is a very interesting calculation in physics to try to understand this, but eventually one gets planets, a lot of the material is blown away, and we are left with a solar system again. Now, much of what you see here, we've learned about because of molecules, and molecules as probes. The molecules, of course, in different regions are different to some extent. The chemistry is different. If density is higher and density is lower, temperature is higher, temperature is lower. And so again, molecules, besides being interesting in and of themselves, are probes of different types of sources. And especially this picture here of actually what would be the cycle between low mass stars like the sun and clouds. All right, here's a real picture of protoplanetary disks. They are dark and they are surrounding young stars known as T Tauri stars. These stars actually have tantrums and are sometimes called adolescent stars. They give forth bursts of X-rays. In any case, again, if you want to see molecules in the disk surrounding the star, you can't do this pretty much in the visible. You need to do this in the radio or also in something called the infrared. All right, that's enough astronomy. Now a little bit of chemistry for the people not trained in the subject. Of course, chemistry is the study of atoms and molecules, and I've shown you here a molecule, well-known molecule known as water, H2O, as it's sometimes written by chemists, although HOH, which is rarely written, would be a better way of describing this molecule, although it does have a bent shape. Remember, all atoms have electron clouds surrounding heavier nuclei, which are very small, but much more massive than the electrons. And when they form individual bonds, you can depict them as having the spheres of electrons actually overlap to some extent. Or another way of doing it is to show these strong lines here called bonds. So this is what a molecule is about. And this does tell you something of the structure. It actually has an angle here. It's not just a linear species. All right, one final thing. The electrons here tend to move up towards the oxygen, and that gives them more of a negative charge than with the hydrogens. And that means they have what's called a dipole moment. And that's very important because radio astronomy of molecules pretty much requires that the molecules you're looking at have dipole moments. Otherwise, you do need another technique to look for molecules. All right, molecules undergo chemical reaction. Here are two simple ways of trying to illustrate a reaction. This is in the gas phase where the trajectories are typically linear, trying to go in a straight line, and then except when they get close to one another. So in this simple reaction here, an oxygen atom reacts with whatever B stands for by stealing B away from C, making a stronger bond, OB, and throwing C unwanted away somewhere. Or you can depict it, if you wish, with spheres, and the overlapping spheres make molecules, and here the green atom ends up bound to the red one, and the purple one goes off. Now that is relatively simple. I mean, it's not simple, but it's relatively simple. If you want complexity, what happens on dust particles, which is very important, also is much more complicated. First of all, it's easier for us to see molecules in the gas, so we don't want them to stay on the dust particles. So it's a three-step process. First, diatoms here and atoms are shown accreting, that means sticking to a dust particle and undergoing a reaction. The reaction is a rather complicated procedure because, as you see here, the surfaces, if you can imagine these surfaces, they're not flat, okay? They're anything but flat. And so the motion of the atoms and molecules is almost a random drunken sailor problem. That's what we mean by diffusion. Okay. So eventually molecules do come together and react. And if the dust has become hot near a star, in the meantime, it can actually, the molecules that are formed can actually evaporate, which is called desorption by people who study this type of thing. On the other hand, if it stays cold, it is still possible that some molecules will come off. Not too many, but some. And that is if they undergo a reaction that gives off enough energy to drive the atom or molecule off the grain. All right, now get a little more detail about how astronomers actually see molecules. What they see is the emission or absorption of various types of electromagnetic waves, and mostly, as we'll see, or as I've already said, mostly radio waves. But all electromagnetic waves look the same. And I see at least the slide is working, and we have here a traveling wave. It's supposed to be going at the speed of light. It's a bit slower. With some computers, it stops completely, and then it's called a standing wave. But in any case, here we have a traveling wave, which is disturbance in two separate directions. Well, it's in two dimensions perpendicular to the motion, one with electric fields and one with magnetic fields. The wavelength is the difference between two successive adjacent maxima of crests in each of the magnetic field and the electric field. We also sometimes refer to waves, especially radio waves, with frequencies. Frequency is the number of wavelengths that comes by an observer per second. So if the wavelengths are big, then the frequencies are small, because it takes a while to go between crests. And if the waves are small, the wavelengths are small, the frequencies are bigger. In wavelength, radio waves have the biggest wavelength, then comes the infrared, then the visible, and then the very small wavelength in the ultraviolet. Of these different wavelengths, you can do radio astronomy from the ground. You can do partially a radio astronomy, partially infrared and visible astronomy. The ultraviolet is totally blocked by the atmosphere, and infrared is partially blocked by the atmosphere. And so infrared is a good case for sending a spaceship or sending a satellite into space with a telescope. Okay. Now, what about what types of radiation do we see and what causes them? So here I'm using a diatomic molecule rather than water, and the only thing I've added is a spring. So instead of a line, we have a spring, and that's to show that these atoms actually vibrate back and forth. They also rotate, and then the electrons move by themselves. And each of these motions gives off radiation or absorbs radiation in different regions of the spectrum. So radio waves have to do with rotational motion. Infrared waves have to do with vibrational motion, and electronic motion is seen in the UV or visible, which means it can only be seen in diffuse clouds because you can't see the visible through the dense dark clouds. All right, so now since I've talked about chemistry and astronomy, let's start the historical portion of the talk, at least starting with the observation. So I start from the year 1930. And what was done in the year 1930 or up to the year 1930 for interstellar molecules? Virtually nothing. And so that's why we have questions here. So 1930 is a little too early for us to start astrochemistry. So we moved to the year 1950. So we're going in 20-year intervals now. By the time this year came around, there had been 3 molecules discovered in interstellar space in so-called diffuse clouds. So here's the experiment. Diffuse clouds, remember, let through visible light. So here's a star, and it gives forth visible light, and some of that light is absorbed in the UV at visible, and from the ground, one only really can see the visible portion, and it's the electrons moving that gives the absorptions. Here's a telescope. I believe this is the so-called Yerkes telescope, which was used for some of this. These molecules, in the years they were formed, they are very strange molecules. And some of the identifications were done even without having been studied in the laboratory very well and needed the help of some professional spectroscopists. Any case, CH, CN, and CH+, very, very strange, very small molecules. So nothing much happened for a while afterwards until radio astronomy got going. Now, this is a rather small telescope. It's once at NRAO, National Radio Astronomy Observatory. It has moved to the Arizona Radio Observatory. Anyway, it also seems to have gotten a little bigger. I don't know how it stretched, but it went from 11 meters to 12 meters. We see it in a sunny sky here, so I don't know if it needed all of this covering. Of course, at the NRAO, if it's the one in Charlottesville, where I work, it rains a lot, and so maybe that's an important reason. But in any case, this thing was first constructed and saw first light, as astronomers would say, in 1967. And then there was a breakthrough. Lots of molecules were found in a very short time, around the year 1970. So this was really the start of molecular radio astronomy. And ever since then, every year, 3 or 4 different molecules, new molecules have been seen for the first time. And we're up to now about 200 molecules seen in the interstellar medium. These initial molecules are shown with the names of the interstellar clouds they are seen in. Now, water, okay, I've mentioned. Ammonia was the first. They actually was seen with a different telescope. This is formaldehyde. Carbon monoxide is very abundant. Methanol is an interesting large molecule, okay? I put this at the bottom of the slide just to mention that the most abundant molecule in space is H2, and it had been seen in the UV for the first time in 1970. What I want to talk about a little bit for some amusement is something that astronomers saw, one frequency, and they didn't know what it was because it hadn't been studied on the ground. And so they called it exogen. There was another one, X2ogen, and a third one, Y-ogen. Anyway, exogen. Okay, it was called exogen, but eventually it got understood what it was. So the story of exogen is an interesting one, briefly. So it was only one line, normally, I shouldn't refer to line, one frequency in the gigahertz. Remember, frequencies on Earth and the radio are the kilohertz and the megahertz. So these are higher frequency and smaller wavelengths. In any case, it was called exogen. It was seen by Snyder and Buell in 1970. My research director was just a spectroscopist. He became interested in when he learned about the molecules in space, went for sabbatical, came back very excited, and told me that that's how I would finish my degree if I started working with them. So of course I did. But by himself, he decided that the molecule that was responsible for this frequency was a very strange ion, which is something that's lost here. A positive ion loses 1 electron. And this is a linear species. So the chemist's diagram is actually correct in that sense. But no one had studied it for the most part. And it was not at all obvious why my research director guessed that was the molecule. He first, if you asked him what were the reasons, he said, oh, well, it turns out in rotational spectroscopy with radio waves, you could actually come close to the frequency if you know the bond separations between the atoms. So he estimated those. That was, and then then quantum chemists who study this sort of thing for a living told him he was wrong. So he said, well, maybe this HCO plus was formed by light bombarding a bigger molecule, formaldehyde. But people told him, but Bill, it was seen in a dark cloud. So where was the light? So anyway, he said, I'm right anyway. And you know what? He was right, and all the students, led by me, were completely wrong. So I have now decided, since then, actually, that the good definition for a genius is someone who gets every argument wrong, but the answer right. And he didn't do that just once. It was very, very interesting. Anyway, what happened eventually in 1975, the molecule was seen by another rotational spectroscopist named Claude Woods, who's still active at the University of Wisconsin. And then, of course, you can compare what's coming from space with what's seen in the laboratory. So HCO plus it was. Okay, moving on to later and bigger radio telescopes. This is a very pretty picture of one in Japan. Why did I show this and not many others? Single radio telescopes that refer to as single dishes. Well, they sent me a nice spectrum, so I felt I should show it. For those of you who haven't thought much about telescopes, of course, here it's the radio waves, not the light waves, but the radio waves hit this dish, bounce to here, come through here, and then it's just like a radio. You take what you have and you see what the frequencies are. In a radio, of course, you get music, and in the molecule business here, you get molecules if you know the molecule from work in the laboratory, if you know its frequencies. All right, so here's a spectrum. This is a spectrum in gigahertz. So gigahertz means bigger frequencies, smaller wavelengths, but still radio waves. Smaller wavelengths and bigger frequencies than your home radio. And here are the frequencies plotted. These are the frequencies you see. They're really not straight lines like this. If you spread this out, you see that it's sort of like a radio. You can get a perfect tuning, or if you get a little away in frequency, it's not well tuned. In any case, each molecule has number of these emissions. This is seen in emission because there's no source of radios to absorb behind it. So what do you learn? You learn what the molecules are, because we have now databases with their frequencies. And you learn how much of them there are, because obviously the one that have more intense emission, the more of them. And we also, with a little more analysis, can learn the temperature of the source, the density of the source, or how homogeneous it is by pointing the telescope in different directions, showing again how good molecules are as probes. All right. But I haven't discussed too much the probes themselves, other than the star cloud star cycle. So let's put some years in here. These years are very approximate. It's very hard to say. There are a lot of people studying all of these different types of sources. But here are some dates. So dark clouds, that is the darkish blackish one, was seen in the early 70s. Hot cores. This was a tricky one. If one defines these hot cores as just the high temperatures, and you get the temperature from ammonia, then Ho was the first person to see really hot cores. But if you define them in terms of the molecules that are seen, then there was other people who worked on it. Anyway, so we go up in years to so-called photon-dominated regions, which I haven't mentioned up to now. What they are just regions of a cloud that are near a star. There's an external star right near them. The star shines light into the regions as far as the light will go, that is, and then it can actually change the chemistry near the border of the cloud. by 1995, pre-stellar cores. Pre-stellar cores, by that I mean it's slightly different from cold cores. I hope Paula will agree with me. Anyway, she and others did a lot of work on these things in the late 1990s and later on the fact that molecules in these very cold regions actually accrete onto grades and don't, for the most part, come off. And that being the case, you start losing the gas. And after a while, it's only hydrogen that remains. Very interesting thing. Anyway, but eventually, if we go back to our cycle, which before planets ends at protoplanetary disks, and protoplanetary disks now are very, very popular since they lead to planets. But it wasn't until the 1990s that a lot of work was done on the molecules in these disks. Yuri Aikawa was a postdoc with me in the mid-1990s, but she had done this work in Japan first. Then, well, I used the phrase hot core for that for a warm region in the cycle I showed you before, but really hot cores are more associated with high mass cycles. The low mass ones have been called hot corinos because they're not as big and not as hot. Anyway, and this was first, I believe, was first called the hot corino by Cecilia Ceccarelli. Okay. So moving on, eventually, instead of single dishes, radio astronomers started using multiple dishes and called this interferometry. And of course, now the mother of all interferometers is in Chile. And there's a high mountain valley, and it's supposed to be very dry. Now, you can do radio astronomy from the ground. It's unlike, say, much of infrared astronomy, but it's still better to be in a dry place and a high altitude. And this was supposedly one of the driest places around. I wondered when I saw snow, but in any case, it still is certainly a dry place. And what these interferometers can do for you, as opposed to trying to use one very big radio telescope, is they have more collecting area, and they're relatively easily movable. And in addition to having a high collecting area and being able to see weak sources, you can actually, by suitable movement, make it so that they can get a high spatial resolution. So what that means is, instead of thinking that an object is homogeneous and doesn't change very much, this telescope will tell you that you're quite wrong and that almost everything is very heterogeneous. Here's an older one working at somewhat longer radio waves than the ALMA, which is, I guess, this is an acronym for Atacama Large Millimeter Array. Anyway, a very large array, which is larger than when it was first used, is in Arizona in the southern US. There's a one in Spain, in Noema. And anyway, so interferometry is now a very important part of observational radio astronomy. Gives you, here's showing what I mean by spatial resolution. This is a protoplanetary disk, and I could have shown you a picture with 20 others or so, but I was afraid of taking up too many megabytes that I wouldn't be able to show you these pictures. In any case, so here's one, and take a look. It's fake color because it's radio waves, and in addition, it's not an individual molecule that you're looking at. This is emission from dust. So dust emits a lot of different frequencies. And the yellow color means that, of course, is where there's the star, and the stuff is cooler in the red here. But the key thing is their structure, right? It said there'll be structure, and here there is. That was not seen before in the visible picture. So here we have structure, okay? And some people feel that this is, we're not looking at dust particles here. The dust particles are seen in the red. What we're looking at may be nothing, or it may be dust that has, oops, went the wrong way here. It may be dust that has accreted, it's actually become planets. It would be much harder to see one planet than to see a whole circle of dust. This is still a very contested point. All right, moving on to the infrared. Okay, so the infrared is helped a lot by going above the atmosphere, or at least not operating from the ground, and balloons were used, and we now have a high-flying airplane, Sophia Observatory, that has been very useful. But the best spectra are seen from space, and one of the earliest, probably the earliest, the European Satellite Infrared Space Observatory. And here's one of the early spectra. This is now not in the not in the radio wave region, but in the infrared. That is very important. One thing you can do in the infrared you can't do in the radio is to look at the dust particles and see what molecules are there. And what you see here is an absorption, but you see what's called silicates, and these silicates are very similar to beach sand, and that's what the dust particles are. Now, in addition, there are a lot of molecules here. They're not a lot, but there are a reasonable number. And these are interpreted for the most part as ices. So in a cold region, on top of the silicate, and also there are carbonaceous dust particles, one could have ices. And the ices are mainly water, but also here are some other molecules, carbon dioxide, carbon monoxide, and methanol found on these ices through the infrared study. Okay, but okay, so that was then before this next one, the Herschel Space Observatory. This works in the far infrared. It's another European observatory, and it is now mostly defunct because the coolant ran out. That's necessary after 5 years or so, but did a lot of very interesting work in the far infrared, which is where the infrared meets the radio. Or the radio waves with the smallest wavelengths, okay, come up against the far infrared. Okay. Now I could show you spectra taken with this telescope, but we have to really move on. Here is a very interesting telescope that doesn't yet exist except on the ground. It's a James Webb Space Telescope. It's supposed to be very, very powerful, and will maybe give us a big breakthrough in studying molecules on dust particles. Okay, but it still hasn't gone up each year. There seems to be a delay, so we have lots of questions for the year. Okay. All right, so now I've been talking a lot about these, about the observations. Let's get to talking about molecules. And there are now over 200 molecules in the gas phase, and I can't show you all of these, so I group them into various classes of molecules, starting, and this is just examples, starting with simple ones, often seen in very many different types of sources. These includes molecular hydrogen, includes ions, H3+, and with one of the hydrogens is a heavy hydrogen, H2D+. Anyway, very simple molecules. The next in line, first are carbon chains. These are very strange molecules. In fact, the chemists in the audience probably couldn't believe that you have such molecules. They are indeed linear. They are mostly carbon atoms, and they have very little hydrogen, which is very unusual because hydrogen is the most abundant element. So these are very strange, and they're typically found only at 10 Kelvin. Well, nowadays, they're being found a little in warmer regions, but for the most part, they're formed in cold regions. The other thing that's very important, another important class of molecules are complex organic molecules. They're not complex. It was a bad term, but I can't complain because I think I and Avina van der Kook originated the term. Anyway, these molecules are very boring. Unlike the carbon chains, which are very interesting, these molecules are very boring. Why are they very boring? Because they are in every organic laboratory. They're not exotic. They're stable in the laboratory, unlike these carbon chains. And they are typically, at least when they were first seen, were seen in these hot cores. Now some are seen in cold cores, some are seen even in diffuse clouds. They're all over the place. So one reason for studying them is that they're intimately related to the process of forming stars. And we can tell a lot about star formation by studying these boring molecules. Maybe I'm a little, I really shouldn't call them boring. I did spend a lot of my life as a rotational spectroscopist, and these were the molecules I did study, because it turns out they are very floppy molecules. So they are very hard to study. Not hard to make them, but hard to understand their spectrum, because the floppy molecules, actually the vibrations and the rotations get mixed up. And anyway, so people should be thankful that these molecules were seen by people like me in the laboratory, because of course they're seen a lot in interstellar space based on those frequencies. Fullerenes are very, very large molecules that won a Nobel Prize for a new form of carbon in the laboratory, and eventually were seen in space. Then we have molecules that may even become bigger than these fullerenes, called polycyclic aromatic hydrocarbons. They're based on the simplest molecule, which is called benzene, which has double bonds, are very strong bonds, and here are regular single bonds. And benzene, if you add all sorts of hexagons together, you get these so-called polycyclic species. They're seen in the infrared, but it's very hard to tell one from another. And only recently have some of them been seen in the rotational spectroscopy. Rotational spectroscopy from the radio waves does tell you the structure. And so we know exactly what these molecules are. So it's a very big advance. And for those of you who are chemists, I leave it to see if anyone could guess what C9H8 is. It does have a dipole, because otherwise it would not be seen by rotation. All right. Now, considering that very few astrochemists were around, I think at the bottom of the slide showing the first three molecules seen in diffuse clouds, I guessed that perhaps there were at most 100 astrochemists in the whole world. So I thought it would be interesting to ask now how many astrochemists are in the world today. So I didn't ask Wikipedia, I asked Siri. So Siri told me I can't complete your request. All right. So I asked Siri how many astronomers are in the world today. And Siri said 10,000. And I think that's probably right. But that doesn't tell me how many astrochemists are around. So what's my guess? Well, my first guess is around 1,000. Maybe someone in the audience can give me a better guess. I tried asking people who had lists, telephone lists, email lists of astrochemists, but no one answered. I don't know why. I bet it's very hard, because you have to include chemists sparingly, because there are a lot of chemists who, because they see molecules that someone else then sees in space, might think of themselves as astrochemists. And there are many more chemists than astronomers. In fact, in the US, there are 155,000 chemists in the American Chemical Society. And there are more chemists than there are many that aren't in this society. And this is one country. So if we don't count chemists sparingly, we're probably going to have more astrochemists than astronomers, which sounds crazy. So I don't know how many real astrochemists we have. All right. Now we do some little more history. This is now progress in studying reactions. Reactions are, of course, how molecules are made in space, and chemists are interested in these things. So I've divided this into the reactions into several eras. They overlap to some extent. And for each era, I have the type of reaction, the apparatuses used, some names of experimentalists, and some names in red of theoreticians. So I apologize if I've missed many names, but a lot of people were involved here. The first era is the ion molecule era. That was when many neutral reactions, the standard chemical reactions, were not studied at low temperature because they were thought to be too slow. So people had indeed even studied ion molecule reactions at low temperature, even in those days. So they were clearly very important in cold clouds. And some of the apparatuses, well, Well, again, I'm going to show you a picture of one of these later because I was told I had to show you some experiments anyway. Okay, the next era, well, here are some ion reactions. H3 plus reacts with CO. Believe it or not, it makes HCO plus, but that was not what Klepper thought about, I think. Anyway, plus H2. Eventually what happens as you get to bigger ions is then they react with electrons and they come apart and they lose most of their hydrogen. And that is why, that was the initial reasoning why there were carbon chains, because you lost the hydrogen from carbonaceous ions. Okay, nowadays we know that there are neutral reactions that also make these carbon chains at low temperatures. Okay, so actually this was a long time getting started because chemists really strongly believed that most neutral reactions did not occur at low temperature. And in the early days of astrochemistry, we looked mostly at the low temperature regions. So in any case, eventually these things did become important. I mean, quite a bit of time after the ion molecule era. Again, okay, here are all sorts of experiments. The KROME, by the way, is a French acronym. And I'll show you the picture of that one. And here are some of the well-known people who worked with the KROME, crossed beams, merged beams, a lot of different apparatuses, and a well-known theoretician. And here are some reactions. This is a very strange reaction because it has a big barrier. And that was the problem with neutral reactions. It was thought that they all had, many of them had barriers and so would not react at low temperatures. Barriers being having to say, go over a mountain to react. And so they would get fast only at high temperatures. Well, this was a strange one, which realized people realized they didn't fully understand what was going on, because OH plus methanol does have a barrier, but is faster at low temperature than it is at room temperature. Okay, there are reasons for that, but it took a while for people to understand it. Another very strange type of reaction is two molecules coming together and sticking, sort of, by making a bigger molecule. And the reason they could do that is the bigger molecule, instead of coming apart, gives off energy in the form of radiation. So we've been learning a lot about very unusual reactions. 2000 starts the surface chemistry era. Now, people had thought about it for a while, but we're talking mostly about experimental progress. And this is still an ongoing thing because it's a very complicated system. And a lot of work, though, has been done in recent years. And here I've taken theoreticians from different eras. Clearly, the most important reaction is the two hydrogen atoms coming to make molecular hydrogen. GR stands for grain. And this is a gloated, if you ever look at a book on surface chemistry, the first chapter always says that surface chemistry is so important because it has the most important reaction in the universe. And in a sense it is, because a lot of things that stem from reactions involving molecular hydrogen. All right. Now, here is the picture of this KROME apparatus. And clearly it's too complicated to discuss. It is an instrument that involves nozzles, beams, and these are called Laval nozzles. And for every temperature that you want the molecule flowing through one of these nozzles, you have to put in a different nozzle. So it takes a while to do experiments. This can do both ion neutral and neutral experiments. And nowadays, different special KROMEs are made for each type, and it goes down to about 10 Kelvin in the gas. So it's very useful for low temperature studies. And here are some people that currently use it, or did use it in the past. And it's for the most part, it's mostly British and French people who do this. All right. Now, history of chemical simulations as we get closer to the end here. This is, well, chemists such as myself do. Take lots of chemical reactions, many have been studied and many we have to guess about, throw them in, say, a proverbial box and see what happens. as a function of temperature and density and time. And that's how we try to understand what's going on in all of these different types of sources. Now, this has been done for a long time. We now, if you want to start doing it, there are reaction networks available, and I've written down several here, including a KROME one. And you can start with that and then try to run with various software and run this for what would be, say, such like 1 million years in space-time, but that won't take very long these days in computer time. Then get concentrations, and you can compare them with observations to see how well you understand things. And if you don't understand it well, you will change the density and change the temperature, change the time, this sort of thing, until you do understand it well. And if you understand it very well, you could make predictions even for molecules that are not have not yet been observed. All right, a history of chemical simulations. This is just going by size. The first one I did with Bill Klepperer, we only had 100 reactions involving 30 molecules. That's tiny. We go through a stage here. These were first purely gas phase, and then when we worried about surface chemistry as well, we're getting up to 3,000 reactions and 400 molecules, and the computers are handling it fine. Today, perhaps 10 to 20 different groups, up to 10,000 reactions. And they haven't all been studied, so those of you interested can become an astrochemist and study them, preferably by computer, unless you like to do experiments. Okay. Now, just a few words about, since I haven't discussed that much yet, about ice mantles and chemistry. So here is a grain at low temperature. And what happens is various atoms and molecules stick to it. And it's the atoms at low temperature that move most and come together to make molecules. Very few of them come off, or some do at low temperature. And we make these molecules, and pretty much one eventually is going to lose most of the gas. Until then, it begins to heat up to form a star, and then we get the gas back, more gas. But before that happens, there could be almost 100 monolayers of water, the most abundant species. Okay, so that I think is now reasonably well studied. A lot of people have studied low temperature surface chemistry. We have to say a few words about hot cores. I've been speaking mostly about cold ones, but hot cores, this work, it was done, most of it was done initially by my colleague and former postdoc, Rob Garrett. What we did is just do a review article on it. And this third paper actually discusses the quantum chemistry of trying to understand when some of these reactions actually occur. Now, what's the difference is these reactions, these grain reactions, there are gas phase processes as well, which I don't have time to discuss. The difference between warming up and between the cold gas and cold grains is here you could have reactions not only involving atoms on a grain, but involving bigger molecules. They undergo diffusion, they come together, they react, and what they're best at, it seems, is to make these complex organic molecules, which still are very, very abundant in compared with other regions in hot cores. All right, so that is still probably the dominant view, although there are arguments that I don't have time to discuss much of involving gas phase reactions, especially involving forming these carbon chain molecules at temperatures above the temperatures of cold cores. Okay, modern era, well, we could say many things, but I think very important are ALMA studies showing us such detail, spatial detail, that I'm tempted to say that no source anymore is ever going to be called homogeneous. And that makes it very difficult for modelers such as myself when we have to just not come up with one temperature and one density, but we have to worry about the source having lots of different temperatures and densities. Other thing very, very, very important now is finally, after many years, being able to detect aromatic species, even with old telescopes, such as, well, it's not that old, but a single dish, not an interferometer. And what is unclear right now is how these molecules are formed, these molecules building up on benzene. How are they formed? Some people even feel that they're not formed from smaller molecules, but they're formed in top-down processes from bigger ones. Other thing now is other things being studied right now. Faster ways of having faster reaction rates on grains. One of which is radiolysis. That's if cosmic rays, high energy radiation, blast grains. Blasts, in radiolysis is mostly protons. The protons hit a grain that has some carbon and ice in it along with water. And many experiments have been done to show that the COMEs are formed. So people are trying to, and this is mostly work now from a former student, Chris Schingeldecker, trying to see if we could actually take this work and understand what's going on in space by theoretical arguments. Another type of improvement in motion and reaction rate on grains has to do with the short range motion, in which unlike regular diffusion, which is long range and has going all around the mulberry bush, the short range motion can be very direct and can be faster. And this is based partially on experiments also from the Linnitz group in Leiden on showing that the molecules are made much faster on a surface than one would think possible. And the detailed theory, again, by Rob Garrett and the graduate student Jin on this business. Finally, there's much too much. We need another hour of work on all the work that's being done now in protoplanetary disks and planet formation, which certainly is now the emphasis of many astrochemists. And finally, the future, we have this beautiful picture of the square kilometer array. Supposedly it's to see first light at 2027. And to exist, I believe there's still plans to have two existences, one in Australia and one in South Africa. Many countries involved, very, very low frequencies. So we're talking here of, almost in the FM radio range. And what is this good for? Well, a lot of it is good for cosmology, looking at things far away from us at the edges of the universe. And they claim also that this should be very useful for astrobiology. As far as astrochemistry goes, lower frequencies are what you expect to see from bigger and bigger molecules. So that's another possibility. And that is an end to the talk. If I can go back to this, acknowledgements to the people who did the work, at least some of the people who did the work, and the ones who paid for it. Thank you very much. And I hope you have some questions.
Many thanks, Eric. This was a wonderful, very comprehensive talk on astrochemistry. I really enjoyed. We wait for some question. Please write in the chat. I can start with one question just to trigger discussion. So, what are in your opinion the bottlenecks that we have now in the astrochemistry field, and what is the next step? Yeah, that's
right.
a very challenging question, but yeah.
Yes, I'm really bad at predicting the future, and I was thinking of a slide saying that I was really bad at predicting the future, but I didn't want to make it clear. I didn't want to say that all of these things I talked about were understood. Okay. So, for example, there is still a lot that's not understood about what happens on surfaces, and much more work is needed. For example, we know what neutrals do on surfaces. We don't know what ions do. Okay? We could have ion molecule reactions, maybe on surfaces, maybe not. I mean, this is clearly very poorly understood, and that might be very, very important, just missed. The other process, I actually showed you one example. There's been no experiment to do this that successfully, and that is this radiative association, a very exotic reaction that can only happen at low densities, in which two species actually in the gas come together and stick by giving off radiation. No one has ever seen this radiation, so this is theoretical. And I know of one person who's now dead who had done an experiment that was close to seeing it, but it wasn't 100% sure he did. And there's one person now I know in the world, and she's trying to do it, but still trying. So, and that's not the only process we're going to find. There are very unusual processes and in very unusual conditions. There were a lot of work on the formation of planets. I mean, a lot of people working on it. That doesn't mean that we fully understand where the chemistry comes from. It might, might have come from protoplanetary disks. On the other hand, it might have to have started all over again when planets were formed. That's still a problem. Astrobiology, of course, is the biggest of all problems. All astrochemists will say that, this is needed to try to understand how life formed. Okay. What what telescopes will do in the future, it's really hard to say, but I'm not sure. Maybe there's someone in the audience who's much more knowledgeable about this square kilometer array and what are the very dramatic things will be done with it.
Yes, thanks. So yeah, we have a few questions. I can continue sharing this. One question is, will be interesting to add some aspect or to tell something about AGN related chemistry.
Yes, I know. I didn't. It's hard to do all of this, and yes, I did some of the early work with Tom Miller, but he now works with a Belgian woman, Lien de Sien, and they have really improved their models a lot. So AG, especially the carbon-rich ones, but yeah. So there is it's not true in the audience that it's not true to say that molecules don't exist in stars. There are certain stars that are carbon rich and in their outer envelope are very rich in molecules too. Almost as rich, and similar to this TMC1. So yes, that's yet another field, right?
So you're receiving a lot of congratulations, Eric, for your wonderful talk. So I just want to report to you this. We have another question, more or less on the line of what I asked before, by Giovanni Sabatini. He asked what the highlights and the next frontiers to be crossed in the near future for those studying astrochemistry. So we go back to the previous question.
Right. I'm sorry, did you say what are the topics or? I didn't hear the beginning of.
Yeah, what is important? Or what are the new frontiers to be crossed?
Okay, yeah. That is a very good question. I guess I answered that when I answered you, Stephanos. Anyway, it's really hard to say, but certainly, we could certainly go to a lot of different types of molecules if we could find them. I think the new when it gets up, the new space telescope for the infrared from NASA may indeed open up what really, much more information than we have about dust particles in space. And many more molecules, no doubt, will have spectra on the ice. The problem is it has been harder to detect them. So right now on the ice, we don't have anything that's really very exotic. We don't know much about ion chemistry. There's a lot of this that probably in 5 years will be done. I was trying to think about it the other day, and I emailed a well-known surface chemist who does astrochemistry, and he said that was funny because he was trying to build an apparatus that would also study how ions react on a surface, especially an ice surface, that water ice being the abundant molecule, the most abundant molecule on these ices at low temperature. And frankly, just nothing, very little is known about the dynamics of it. Some of the potentials are known, but anyway, there's much more to be done.
Right, thanks. So another question from Klaus Paszek. What do you think of how much more will JWST allow us to look deeper into dark clouds and star-forming regions with protoplanetary disk?
Yeah. Well, we'll see. Yeah, it certainly should do that. It's very powerful. Now there's also it's powerful in one way and not in other ways. It probably, with vibrational spectroscopy, which is what it will do, if it were looking at gas phase molecules, you could actually see rotational substructure. So you could get both rotation and vibrational spectroscopy done at the same time, but you need high spectral resolution, and that is sort of marginal with that telescope. It's actually doable with the airplane, the SOFIA telescope, which is now looking, for example, at the Orion Nebula. It's a cloud, nebula being an old word for cloud, and looking in the mid-infrared and finding molecules. And finding also rotational substructure and seeing some very unusual things. So that's important also. I don't really, I'm not an expert on ice spectra, so I don't know if I want to comment too much on it. But people who are interested in that field really have high hopes for this new NASA telescope when it goes up into orbit. By the way, something I didn't mention that's interesting is that recently orbits have been made not around the Earth, but around the sun, because there's too much noise around the Earth. So one of the telescopes I showed you, the Herschel telescope, was in orbit around the sun. And it will be the same with the infrared telescope.
Yes, we have another question from John Ramsey. Okay, great. Thanks for the nice and comprehensive talks. So do you think there's a particular type of telescope that doesn't currently exist, but will be super useful or helpful to advance astrochemistry? That's a interesting question.
Interesting question. If someone who knows more about the physics of the SKA, that might really make for large detection of large molecules. It's possible. X-rays have not been used to the fullest. I've had these talk with X-ray people that that's a possibility. Mm-hmm. But I don't know more than that. I mean, it's very hard to say.
Yeah. Again, John. Yeah. John has another question. When it comes to understanding reactions on dust grains, do you think we are missing any fundamental physical mechanism, or is the challenge instead the complexity of the problem?
Well, that's a good question. When this group in Leiden, headed by Harold Linnertz, showed that, of course, it's not exactly the same thing as interstellar space, but our theories could also work for the laboratory stuff. The 4 papers published, is just amazing how quickly these bigger molecules get made. Now, they don't require any light. For example, I didn't have time to talk too much about the hot core business, but the molecules that react on grains as the warm-up occurs to hot cores are what chemists call radicals. They are particularly reactive molecules made from others by photodissociation. So photons are actually light is actually required for that mechanism. And it certainly does, that mechanism is only good for forming molecules then at higher temperatures. Lower temperatures, we're still, it's very unclear that we fully understand what is powering Linnertz's, they don't use, they use light sometimes, but it's all thermal. And I don't think it's fully understood. In fact, when I first heard it, I just didn't believe it, but I was clearly wrong about that. But in any case, it's very interesting. And I mentioned 2 possibilities for it, but I'm not sure they are enough to understand it. So this is something new. If you'd asked me this question 10 years ago, I would have said, I think we understood this. We understood random motion as best we could. We do have these Monte Carlo methods to try to do it better, but I don't think it's true anymore. This is why it's so hard to predict the future.
Right. So we have another question from Nicole Gutierrez. How could you explain the chemistry occurring on the surface of grains to a person who doesn't know anything about dust grains and only knows the dust in their house?
Right. Well, if you look at a dust particle, say under a very powerful microscope, or you talk to a theoretician who calculates the potential energy involved in motion, you can get a picture of it. What I used to do when I would give a talk on this subject is, it's not easy to do this with Zoom. I would talk to an audience in a room with chairs. And I would say the chairs are so-called potential minima, which means they're valleys that the molecules would like to stay in. And then in between these chairs, there would be a space. And I would say, well, these are the molecules have to hop from one chair to another. And I made sure that the number of students I had doing these motions was fewer than half the number of chairs, or something would happen. Instead of telling them to do it randomly, I each gave them a different sequence of motions as to what direction they would go from one chair to the next, and from the second chair to the third. And we had a total random motion. And that actually, it didn't do too badly on making the molecules we thought should be made. So does that help?
Okay, so I don't see other. I think so. Yeah. So I don't see other questions, but I have a question. What is your advice for young students who wants to start working on astrochemistry?
Yeah, you mean after they go to university or before? I mean,
yeah, after they start already to.
Okay, so it depends on the country you're in, but there are universities do have PhDs in astrochemistry these days. So you can get a PhD in the subject. And you could, it depends whether you want to do astronomy, you want to be an observer and look for molecules with radio or infrared radiation from space, or you want to do chemistry and figure out new reactions, what happens with different physical conditions. I mean, at our own university, we have people who do all of these things. So you can choose then. What is popular in one era may be quite different than what's popular in another era. But there are a lot of European, not a lot, but certainly there are a lot of programs like this in European countries. So and it's improving in the US as well. There are several universities now that have these degrees.
Okay. So,
but what exactly you want to study, well, no, I don't know. I don't want to give that information away even, but I'm just joking on that, but it really depends what your interests are. It is a very big field these days, so that a lot of things you can do.
Right. We have now a quite specific question. We are going into technical question now. Elliot Reedy is asking, is it possible that the interesting carbon chain molecules form through a top-down pathway?
I would never say anything is impossible, but yes, it's possible. The only problem I have with the top-down method yet isn't as detailed as the bottom-up ones. But I think though the carbon chains, we don't have a problem explaining it. I think as much as we do with now we see things like KROME at low temperature, and the theories we have for it are only for high temperature. Now, we don't fully understand it for low temperature, and I've heard several talks in which people claim it's a top-down mechanism that we've missed. So yeah, maybe. But I don't, it's there are things we don't understand at all. For example, I give a talk about these KROMEs, all about them, showing that they're all over the place, and they even exist in clouds that one would almost call diffuse. And that's really hard to understand because the densities are very low, and it's very difficult to understand how that could happen. And so it is quite possible that there's a top-down mechanism there, and people do suggest it. So yes.
Yes, actually, Elliot was mentioning that after the discovery of C60 and C60 plus, perhaps a top-down pathway is what we should look at.
That's right. That's right. And C60 plus is found in a diffuse cloud. C60 and C70 are found in a denser nebula, but or more than one. But C60 plus is very hard to understand.
Okay. Yes, we have an interesting question from Tommaso. Imagine you meet the genius of the lamp that tells you that you can solve only one single problem in astrochemistry. What problem will you choose to solve?
I don't know the answer to that. I think I'm not sure. I don't know.
That's fair enough.
I think I mean one could argue biology. One could try to get some better understanding of at least the start of the formation of very big molecules needed for life forms. That would be something that would be dramatic. As far as the chemistry goes, there are certainly exotic reactions we don't understand at all. And so that's another thing. I don't think it's as exciting as the biological aspect. And but surface chemistry, still a lot has to be done. And who knows? We could find molecules in new places too. It's hard to say.
Right. I think that the question was more like if there is something do you think that can revolutionize the field. Probably this is a better question.
Well, there are certain reactions that might be, if one could understand, say, these association reactions. I mean, that would be a much faster way of synthesizing molecules in the gas phase. Because you couldn't, if molecules just came together and stuck, right? That's faster than any other type of reaction, right? As long as it has a larger rate. And people have failed at doing this, and that would be. Eventually, someone should be able to do it. I mean, other types of reactions that we thought never would be understood are now understood, and. So there are questions still, and surface chemistry, as I mentioned several times, I mean it's a very tricky business. In fact, the surface chemistry we study on cold clouds or in low temperatures in the laboratory is not the same as the surface chemistry that occurs at higher temperatures. Or that chemists typically study in the laboratory, because the low temperature ones are what are called physisorb. They're very weakly bound. Otherwise, they wouldn't move, and you wouldn't have the diffusion. The chemisorb molecules are bound with bonds as strong as molecules themselves, and only at high temperatures would they move. And so as far as I know, there have been only a very small number of papers worrying about what happens on grains at high temperature. And something has to, we see molecular hydrogen formed in high temperature regions, and that has to be on a grain. But no one fully, we don't fully understand that. Along with an Indian colleague, we've tried to write one paper on the subject, but there's a lot we don't know.
Yes, agree. Okay, so I don't see other questions at the moment, but I guess you had quite a variety of questions mainly on the future of astrochemistry.
Right, that's right.
So I think, yeah.
Yeah,
I don't know if you would.
a very hard question to answer. It's of course a very important one, but trying to predict the future of science is not so easy, because it typically goes, not always, but it goes by smaller steps, and the giant steps come very rare, really. And most of us, even if we're well known, are not going to be doing giant steps all the time.
Right. Yeah, but I agree with you that surface chemistry is probably a challenge now, and also considering the new experiments where has been shown that glycine can be formed under cold conditions. I think this is the way to go to understand the origin of life.
That's correct.
Yes. So yeah, I guess we are done, and we thank you very much, Eric, for your time.
You're quite welcome.
For your nice talk. And yes, thank you all for being with us.
Thank you for having me.